The biggest trap in the quantum internet is the name itself. It sounds like a new internet, or instant privacy, or faster communication. In reality, the hard problem is much narrower and much more useful. It is the reliable extraction, transport, and use of fragile quantum states under real engineering constraints. Start with where the field is closest to deployment. That is quantum sensing. Sensing is not about showing off a quantum computer in a lab. It is a measurement discipline. The value proposition is improved estimation, better detection probability, and higher signal-to-noise in regimes where classical probes hit a wall. That sounds abstract, but it forces the right question. What exactly is the variable you want to measure? In what environment? With what uncertainty budget? This is where many quantum advantage claims rise or fall. Quantum metrology is the framing that keeps everyone honest. You do not get credit for saying quantum enhanced if you cannot specify the noise model. You do not get credit if you cannot state the baseline classical sensor. And you do not get credit if the effect disappears outside controlled conditions. The practical work is calibration, packaging, detector characterization, and repeatable operation, not only clever state preparation. Quantum radar is a good example of why discipline matters. It is often described as if quantum automatically means superior detection. The better stance is more cautious. Broad operational superiority in contested real-world environments remains speculative unless field performance, target models, noise conditions, and countermeasure behavior are specified. In other words, if you cannot write down the measurement model, you cannot justify the procurement. Now shift to quantum communication, which is more mature conceptually than many people assume. You can do point-to-point protocol analysis, and you can design constrained deployments. But the security story is never secure because quantum. Security depends on assumptions. It depends on adversary models. It depends on what your devices really do, not what an ideal diagram says they do. Two coupled realities keep showing up. First, channel loss and detector imperfections are not small details. They drive whether a protocol is practicable and what the failure modes look like. Second, key management and classical authentication still matter. Even if quantum key distribution is part of the stack, you still need classical systems to authenticate endpoints, manage keys over time, monitor the network, and handle recovery. Without that, you have a fragile link, not an operational security capability. A useful mental model here is governance by explicit boundaries. Any serious deployment conversation should be able to state in plain language what the protocol assumes, what the devices assume, and what happens when those assumptions drift. Side channels, implementation drift, and finite key effects are not exotic. They are the normal way real systems break. If those are not part of the contract, then the contract is not about security. It is about hope. The third domain is quantum networking, and this is where expectations most often outrun readiness. Networking is not just two nodes exchanging photons. A multi-node network needs interfaces, synchronization, scheduling, routing concepts, memory management, and orchestration across heterogeneous nodes. It also needs a compilation layer, because distributed quantum workloads are not the same as running one circuit on one machine. A peer-reviewed result in 2023 made that point concrete by specifying a modular quantum compilation framework for distributed quantum computing. The headline is not the framework name. The insight is that partitioning and compilation become prerequisites for compute-capable networks. Once your computation spans nodes, you are managing unequal fidelities, unequal gate capabilities, channel loss, and the finite lifetime of quantum memory. That is a systems problem, not a physics demo. This brings us back to what the quantum internet actually means here. It means a network capable of distributing quantum states, or entanglement, between nodes. It doesn't mean faster than light signaling. It is not a replacement for the classical internet. And it is not a general privacy solution without protocol-specific assumptions. Those negations are not pedantic. They are strategic, because they prevent category errors and capital allocation. The integration reality in 2026 is hybrid systems, end-to-end. Classical control planes do the heavy lifting around the quantum parts. They handle timing, routing decisions, calibration procedures, authentication, monitoring, logging, and recovery. If you cannot operate the classical plane reliably, you cannot claim you can operate the quantum overlay. In practice, the quantum channel is often the most delicate component, but the classical control layer is what turns a delicate component into a service. So what separates a demonstration-grade quantum network from an infrastructure-grade service? The answer is not a single record-breaking experiment. The separation is memory lifetime, synchronization accuracy, and operational reliability. It is repeatable interfaces that avoid bespoke integration each time. It is acceptance testing, logging requirements, and lifecycle support. It is the ability to schedule and recover, not just to transmit once. That is also why standards bodies matter more than they sound. You need shared definitions for interoperability and conformance, especially for quantum key distribution systems and their integration into broader security architectures. You also need clarity about how quantum communication relates to post-quantum cryptography and to classical key management. Overstating any one layer's protection envelope is a real risk. It creates false confidence, and false confidence is a security vulnerability. A practical way to view the timeline is staged and uneven. From 2026 to 2050, sensing instruments tend to mature fastest. Quantum communication can be useful, but mainly in specialized security contexts with tightly bounded models. Quantum internet work stays heavy on testbeds, standards, and interface definition. In the mid-horizon, roughly 2050 to 2100, quantum network services may become durable niches, but only if memories, repeaters, interfaces, and operations cross serviceability thresholds. Past that, in longer horizons, quantum links and sensors can become embedded subsystems for timing, navigation, sensing, and scientific instrumentation, without ever becoming the dominant layer for everyday consumer traffic. That last point is counterintuitive but important. A general-purpose quantum internet serving broad consumer traffic by 2050 is not established by the evidence here. The plausible path is specialized service layers, not universal replacement of classical networking. Quantum networking can still be strategically decisive, even as a narrow layer. Think of it like precision timing, or high-assurance key material, or distributed scientific measurement, rather than a new social network backbone. From an investment and procurement perspective, the discipline is straightforward, even if the technology is not. For sensing, allocate budgets through measurement contracts, not technology slogans. Specify the target variable, the uncertainty budget, the operating environment, calibration intervals, false positive tolerance, and maintenance labor. For communication, demand security claim discipline. Every engagement should state the protocol assumptions, the adversary model, the device assumptions, the key management workflow, the classical authentication layer, and the failure modes. For networking infrastructure, fund interface and conformance work before scaling corridors. Multi-vendor deployments without acceptance tests and control plane definitions become expensive science projects. Treat any quantum internet proposal as an infrastructure option, not a near-term replacement. Stage-gate investment by entanglement distribution performance, memory lifetime, orchestration reliability, and serviceability. One more strategic implication often gets missed. You need internal capacity to evaluate hybrid quantum classical systems. That means people who can read metrology specifications, quantum protocol assumptions, telecom integration documents, and cyber risk language in the same review process. If those skills stay siloed, the organization will buy impressive components that do not compose into a dependable capability. If you want a final filter, ask 3 questions. Where is your measurement bottleneck right now that can be tested against a classical baseline with a written uncertainty budget? Which vendor security claims quietly rely on idealized assumptions that your real devices and operators will violate? And will you shape standards and conformance early or accept vendor-defined interfaces later? The memorable line is simple. Quantum advantage is real only when it survives loss, noise, calibration, and governance, because that is what turns a phenomenon into infrastructure.